Hello, everyone. Good morning or afternoon. My name is Divakar. I have over 15 years of experience in IT industry, and I'm currently serving as an architect in aviation industry. And I'm excited to share the insights on a transformative shift happening quietly but powerfully within the aviation industry. We are at a pivotal moment where traditional maintenance models are being reimaged. Behind the scenes, a technological revolution is underway, one that's redefining how airlines maintain and manage their fleets. At the heart of this transformation is digital twin technology, a powerful enabler of predictive platforms that allow us to anticipate issues before they arise, optimize maintenance schedules, and enhance operational safety and effective at scale. Today, we will explore how these digital twins are not just improving maintenance, they are reshaping the very foundation of aviation operations. Let's begin with understanding what a digital twin truly is. It is not just a 3D model or dashboard, it is a living, evolving virtual replica of an aircraft's physical systems. This replica continuously updates itself using real world data, making it a dynamic reflection of the aircraft's current state. The foundation of this revolution lies in three key capabilities. First, data collection. Modern aircrafts are embedded with thousands of sensors that generate massive volume of telemetry. Second, dynamic simulation. These platforms recreate real world conditions virtually, allowing engineers to scenarios and monitor system behaviors without touching the aircraft. Third, most importantly, predictive maintenance. Digital twins can anticipate mechanical failure week in advance, enabling proactive interventions that save time, cost, and improve safety. This is not just a technological upgrade, it's a fundamental reimaging how we monitor, understand, and maintain complex aviation systems at scale. Modern aircrafts are no longer just machines, they are flying data centers. Thousands of sensors monitors everything from engine performance and cabin pressure to structural stress and fuel efficiency. This creates a massive stream of telemetry data every second. But collecting data is only the beginning. To extract meaningful insights, we need sophisticated ingestion architecture systems that can handle diverse data formats, varying frequencies, and inconsistent quality levels. That's where its computing comes in. Initial data processing happens on board the aircraft, condensing raw telemetry into actionable insights before it's transmitted into ground systems. The quality and completeness of this data foundation directly impacts the accuracy of predictive algorithms. Robust platforms incorporate data validation, routines, anomaly detection, and quality scoring mechanisms to ensure that the data feeding our digital twins is reliable, consistent, and trustworthy. In short, the strength of our predictive capability begins with the strength of our data foundation. To support predictive maintenance at scale, the architecture behind digital twin platform must be both flexible and resilient. We start with container-based architecture, which allows to deploy analytical workload dynamically. This ensures that different processing pipelines remain isolated, secure, and efficient. Kubernetes orchestration plays a key role here. It enables the platforms to scale computational resources based on real-time demand, ensuring performance even during peak data load. Next, we have a hybrid data processing. This combines stream processing for real-time monitoring with batch workflow for deeper analysis. It's especially important when handling time series data and large binary flight recordings. that vary in frequency and format. For storage, we use tiered strategy. Hot storage provides immediate access to recent data. Warm and cold tier store historical data used for trend analysis and model training. And finally, security is woven into every layer of architecture. Given the sensitivity of our aircraft operational data, we implement zero trust networking, encrypted data transmission, and robust authentication mechanism. These measures ensure that the platform meets the straight safety and reliability, the standard required in the aviation. One of the biggest hurdle in implementing digital twins platform is legacy system integration. Airlines operates within complex ecosystem like maintenance management systems, inventory control platforms, scheduling tools, and regulatory compliances application, all of which have been in place for decades. Bridging the gap between these older systems and modern digital twin platforms requires careful architectural planning. We need robust integration framework that can translate between different system languages while preserving data integrity and operational continuity. This is where API design becomes critical. Well designed APIs abstract the complexity of legacy integrations and interactions, offering cleaning, reliable interfaces for a digital twin platforms to access, like historical maintenance record, parts inventory level, schedule maintenance windows. By building these bridges effectively, we ensure that the digital twin platforms can operate seamlessly within existing airline infrastructure without disrupting workflows or compromising data quality. Real power of digital twins perform their predictive analytics capabilities, right? These platforms take raw operational data and transform into actionable maintenance insights. The insights that helps us anticipate issues before they disrupt operations. At the core of this transformation are machine learning algorithms trained on historical failure pattern and operational conditions and maintenance outcomes. But it's just about identifying isolated issues. It is not just about identifying isolated issues. Aircraft systems are deeply interconnected. A failure in one component can cascade across multiple systems. Effective digital twin platforms model the systematic relationship, giving maintenance team a holistic view of how individual component health affects overall aircraft availability. The predictive process unfolds in four key stages. Stage one, historical data collection. We capture wide range of operational conditions and failure modes to build a rich data set. Second stage is model development. Algorithms are trained and detect subtle indicators of impending issues which are often invisible to traditional diagnostics. Stage three is validation and refinement. Models are continuously improved using real world maintenance outcomes, ensuring accuracy and relevance. Stage four is actionable insights. The system delivers specific, timely maintenance recommendation, which empowering team to act before problem escalates. This is where digital twins truly shift the paradigm from reactive maintenance to proactive, data driven decision making. To truly enable predictive maintenance, digital twin platform must operate in real time, and that's where edge computing becomes essential. Let's break it into three layers. First, aircraft based edge computing. This performs initial data analysis during flight, detecting anomalies that may require immediate attention even before the aircraft lands. Second, we have ground based edge computing. These systems take over once aircraft is on the ground, conducting more intensive analysis and generating detailed maintenance recommendations. Third, we rely on centralized processing. This layer coordinates insights across the entire fleet and performs deep historical analysis during off-peak periods, helping identifying long-term trends and systematic issues. Now, because of this is a distributed architecture, it requires sophisticated coordination. Platform architects use event-driven architecture and a message queuing systems to ensure that insight generation across different nodes remain consistent, synchronized, and up to date. This is multi-layered approach ensures that maintenance decisions are both timely and informed, whether the aircraft is on in the air, on the ground, or part of global fleet. In aviation, safety is non-negotiable, and digital twin platform must operate within one of the most tightly regulated industries in the world. Regulatory bodies like the FAA in the United States and EASA in Europe enforcement training requirements around maintenance practices, documentation standards, and system reliability. These mandates every aspects of platform architecture. For example, platforms must implement meticulous data retention policies, preserving maintenance records for decades to support audits and investigations. Additionally, platforms must maintain comprehensive audit trails, documenting every predictive recommendations and the coordinations and corresponding maintenance action which taken. This level of traceability ensures not only compliances, but also accountability and trust in the system's recommendations. Ultimately, regulatory compliance is not just a checkbox, it's a core design principle that ensure digital twin platforms uphold the safety standard critical to aviation operations. To see digital twin technology in action, let's look at Lufthansa Systems, a leader in applying these platforms at scale. Aviator platform is one of the most comprehensive implementation in commercial aviation, showcasing how platform engineering can transform maintenance operations globally. They built a comprehensive data foundation, using enormous volume of operational data from their fleet. This enabled the creation of detailed digital replicas that evolve continuously based on real world conditions. Then they tackle legacy systems integration. Through carefully designed API layers, Aviator translated between legacy formats and modern platforms capabilities, ensuring seamless access to historical maintenance record, inventory levels, and scheduling data. Most impressively, their predictive algorithms have demonstrated validated accuracy, identifying component issues week before traditional inspection would have caught them. Lufthansa's success highlights the transformative potential of digital twins when supported by strong engineering, thoughtful integration, and data-driven decision making. One of the most exciting advancement in digital twin platform is integration of augmented reality or AR. AR brings digital twin insights directly into the technician's physical workspace, overlaying real-time data into actual aircraft components. This means technicians no longer need to flip through manuals or switch between screens. Instead, they can follow step-by-step visual instructions, identifying components instantly, and receive safety alerts all within their field of view. The result? Fewer errors, faster repairs, and greater confidence in maintenance execution. Advanced AR systems go even further by incorporating live sensor data from the digital twin. This allows technicians to see component health, performance trends, and even predicted failure right as they are performing at the task. It's powerful combination of data visualization and precisions. And it's redefining how maintenance is performed in the aviation industry. As a digital twin platform scale globally, they must adapt to wide range of operational environments, regulatory frameworks, and cultural context. Let's start with global data collection. Platform aggregates insights from fleet operation operating under different regulations and conditions, creating a rich, diverse data set that enhance predictive accuracy. Then a fleet level analytics. These tools help identify systematic issues and compare performance across similar aircraft types, regardless of where they are flying. Time zone coordination is also critical. Maintenance decision made in one region must account for operational impacts across the global, especially for airlines within interconnected schedules. And when it comes to our communication infrastructure, platforms must adapt to varying connectivity levels. This is achieved through local caching mechanisms, ensuring that insights remain accessible even in low bandwidth environment. Finally, a successful global implementation requires thoughtful localization. That means designing user interface and training materials that accommodate diverse languages and cultural norms so that maintenance team everywhere can fully engage with the platform. In short, global coordination is not just about technology. It is about making the technology accessible, adaptable, and effective across the borders. For digital twin platforms to operate effectively at scale, they must highly optimized, both in terms of performance and cost. Let's start with performance optimization. We use database optimization techniques to balance fast query performance with effective storage. Dynamic scaling ensures that the platform can handle fluctuating analytical workloads without over provisioning resources. Intelligent caching speeds up access to frequently used reference data. And network optimization ensures smooth operations across global sites, even in a region with limited connectivity. Now, let's talk about the return of investment, which is where the real world business value comes in. By reducing unscheduled maintenance events, we avoid cost of AOG situations that can run into thousands of dollars per hour. Inventory optimization become possible through more accurate demand forecasting, reducing excess stock and shortage. Labor costs go down thanks to better scheduling and faster diagnostics. And finally, we extend component lifespan by performing maintenance at optimal time. Not too early, not too late. Together, these benefits make digital twin platform not just a technological upgrade, but strategic investment in operational excellence. As digital twin platforms continue to evolve, we are entering a new frontier of technological innovation that will further transform aviation maintenance. Let's start with advanced AI capability. We are moving beyond predictive maintenance into autonomous planning, parts procurement optimization, and even robotic execution of preliminary maintenance tasks. These AI driven systems will streamline operations and reduce human workload. Next, quantum computing, which is one of the horizon. It promises to unlock highly sophisticated optimization algorithms is capable of evaluating thousands of variables simultaneously for maintaining maintenance scheduling and resource allocations. This could dramatically improve decision making speed and precision. Blockchain technologies are also gaining traction. They offer secure, transparent solutions for maintenance record verifications, part prevents tracking, and multi party data sharing across airlines partnerships, which enhancing trust and traceability. And finally, The Internet of Things is expanding. IoT. Future aircraft designs will feature denser sensors network and higher measurement precision, providing even more comprehensive data foundation for digital twins platform. These emerging technologies will not only enhance platform capabilities, they will redefine how we think about aircraft health, maintenance strategy, and operational efficiency in the years to come. Digital twin technology has fundamentally transformed how the aviation industry approaches maintenance. We have shifted from a reactive response, where issues are addressed after they occur, to proactive interventions that prevent problem before they impact operations. But successes in implementing these platforms goes beyond technical sophistication. It requires organizational commitment to change management, workforce development, and process transformation. As the technology mature and expand into new domain, the foundational principle established in aviation like safety, reliability, and operational efficiency will likely guide adoption across other industries. Aviation's pioneering work with digital twins demonstrates their transformative potential when engineered and deployed at global scale. This is not just a technological evolution, it's a strategical shift in how we think about asset management, operational resilience, and future readiness. Thank you all for your time and attention today. As we have seen, digital twin technology is not just a tool, it's a transformative force reshaping aviation maintenance from the ground up. From predictive analytics and edge computing to global coordination and emerging technologies, the journey ahead is both exciting and full of opportunity. I hope this session has sparked new ideas and perspective how engineering platform can prevent innovative. Thank you all